the only organizer.
Okay, now we are recording, I see. Okay, perfect. Well, it's already 4:01. Hello and welcome, everybody, officially. My name is Florian Kutschat. I'm the CEO and programmer of AnalyzerPro. And this is our 2026 Summer's Digital Summit. We do these digital summits twice a year in order to connect the people from all over the world who work in the very niche field of traffic accident forensics with each other, so everybody can learn something from a colleague from a different place in the world. And today I'm very happy and honored to have Eugene Liscio with me from Canada. Eugene was best known to me for his Recon 3D software, which can be used for LiDAR scanning on iPhones, and then importing those scans and doing all kinds of things that he is now going to talk about. Eugene, please, you have the floor. It's about 50 minutes, and afterwards, everybody can ask questions to Eugene or me. Better ask Eugene. And I hope everybody gets something out of this summit. Eugene, the floor is all yours. Thank you.
All right. Thank you very much, Florian. Yeah, thank you for the invitation, Florian. Thank you to Lisa for helping to organize all this. She's been great for communication and helping me out. So welcome, everyone. Thank you for being here today. It's a pleasure to be speaking with the AnalyzerPro team here. And what I'm going to do today is just kind of go through a number of different technologies, not just iPhone LiDAR, but a few other things. And then we'll sort of bring it together and talk about iPhone LiDAR. But let me get going here because I do have quite a bit of information here. Just a tiny bit of background before I begin. But as Florian mentioned, Recon 3D is something that I started more recently, but my actual sort of main work has been doing consultancy in the area of crime scene reconstruction, that sort of thing. I did do quite a little bit at the very beginning with collision reconstruction and that sort of thing, but it just evolved very quickly over to the crime side, just through a series of people that I had met and cases and things like this. So I now primarily do a lot of crime scene reconstruction work, bullet trajectory work, bloodstain pattern analysis, and things like that. So yeah, there's other things I'll talk about, like the Recon 3D and Vision 3D. We'll definitely get into that in a little bit more detail. And what I have planned today is to talk about a number of 3D technologies in forensics. And part of the reason why I want to talk about things like LiDAR and photogrammetry and such is because Recon 3D, the technology behind it, is actually two technologies that are sort of fused together, and they help each other to get really good data, at least from a phone anyway. And but what we'll do is we'll talk about the documentation part, then we'll talk about different kinds of things you can do with it, so applications and things in AnalyzerPro, and then we'll also get into the visualization side, being able to present that data, that evidence, the analysis, whatever that might be. So we're going to start off and get into the documentation technologies for forensics. So there are a number of different technologies that I'm showing here on my screen, and I've listed them in chronological order. So on the left, we have photogrammetry. And as we move to the right, like our iPhone LiDAR, that is like one of the more recent ones, let's say. Now, photogrammetry being by far the oldest technology, starting in around the 1850s. So when the first cameras were made, there was a Frenchman who said, I think I can use this for mapping and surveying. And, we talk about drones and things like that today. Well, guess who was doing that back in the 1850s? People were putting these huge cameras on these hot air balloons, flying them over France or whatever, and then taking photographs and then using the plates to actually do some calculations and geometry and perspective stuff, and basically being able to get contour maps and things like that, which is pretty cool. Total station, very important tool from the 90s, starting in the 90s. Laser scanner, we'll talk a little bit about that. Structured light scanners are another type of scanner which is being used, but probably not going to talk about that one too much. And then, of course, the iPhone LiDAR, which is going to be primarily what I'll be focusing on. But if we had to narrow this list down, what I call the holy trinity of 3D forensic documentation, it would by far be photogrammetry, would be the total station. And when I say total station, I do also mean GNSS, because that's something a lot more recent that people are using. So something, for example, like this that I have here, it's a little MLID RX, low-cost tool, but gets you centimeter accuracy, almost anywhere on the planet if you buy the service or whatever, just a service through a phone, pretty cool. And then, of course, the laser scanner. So those three are still very, very popular technologies. Now, if we want to regroup these by how they work, photogrammetry is its own thing. So the basis of photogrammetry is very unique, and it's different from LiDAR, obviously. Now, the total station, the optical part of the total station that emits a laser, the laser scanner, and even the iPhone LiDAR are light-based, but they work on a principle of like time of flight or something like that. Now, they are structured differently in some ways, but they do have sort of a basic principle, which is the same, which is LiDAR. And then, of course, structured light. Now, structured light is completely different. I'm not going to talk about that one, but usually you're emitting some kind of a pattern, like a black and white stripe pattern, or you're doing something in the infrared range, which is a unique repeating pattern or something like that, okay? But that's what we got there. And we're going to be focusing in on these three things: laser scanner, photogrammetry, and iPhone LiDAR. So let's start with the terrestrial laser scanners and LiDAR. So let's begin with LiDAR. What the heck is LiDAR? Now, some of you that, if you're working in policing and you've got a radar gun or one of these LiDAR guns, you probably know that you can get speed from vehicles. And LiDAR stands for light detection and ranging. So it's a portmanteau. So LiDAR, sonar, radar, detection and ranging. That's the important part. Now, the basic idea here is that if we emit a signal, and that signal can go and bounce off an object and then come back. So basically, you throw something, it bounces off of a surface, and then when the part of the signal returns, you capture that. If you compare the outgoing signal to the return signal, you can tell something about that particular object. Now, in our case, we're typically interested in how far it is or the position of something, but you can tell other things. So, for example, when you're doing aerial LiDAR and you're flying over a forest canopy, depending on the wavelength of light that comes back, you can say something about the type of vegetation that's in that forest. So there's this extra little piece of information that you get depending on the wavelength that you're going to be using. Now, very important to laser scanning is the laser. And I won't get deep into the laser structure or whatever, but there's two things of a laser that make it quite unique. One is something that's called coherence, and coherence is the ability to keep that focused beam. So if you have a laser pointer, you know that you can be 100 meters away from something, and if it's at nighttime and you point the laser at a wall or something across the street, well, you still see quite a narrow beam, which is really interesting. It's not like the lighting that's around in my office where it just gets emitted in all directions. So it's a very highly focused beam. The second thing is that the laser can be monochromatic, meaning mono meaning signal, chroma meaning color. So it emits a very specific wavelength of light. So if I want a red laser, a blue laser, a green laser, an infrared laser in a specific range, we can tailor the type of wavelength to the application that I'm going to be doing. So if a higher wavelength is better in one application than the other, we can do that as well. So the laser is super important to the terrestrial laser scanners. Now, as humans, we see actually in a very, very narrow bandwidth of the electromagnetic spectrum. So you can see here in this table, I've got gamma rays, X-rays, UV, infrared. And so humans see somewhere in between UV and infrared, okay? So somewhere between like the 400s and the 700 range, that sort of thing. It's a very, very small range. And as we approach 700 and past 700, we're going to the infrared. So infra beyond the red colors, which is the 700. And that's typically where most laser scanners are going to work. So this is just a quick table here looking at some different scanners. And you'll see on the wavelength, 1550 is a very common wavelength now. Now that wasn't the case around 2010. This is something that evolved, around 2012, 13, 14, and people started realizing that if you go up higher in the wavelength, you can choose this 1550 nanometer wavelength, which is very beneficial. And it has to do with the fact that this particular wavelength gets absorbed by moisture in the atmosphere. So if you imagine you have a flashlight during the day and you're pointing it outside when it's bright and sunny, you're not going to see the beam across the street because you're fighting with the sun. But 1550, very little 1550 or less of 1550 nanometer gets to the ground. And so if the laser scanner is using 1550 and you're only looking for 1550, it's like having a flashlight at nighttime. You can see the beam from much farther. So there's some advantages there. Now, there's a whole bunch of different laser scanners out there, different manufacturers, and actually, it's really interesting because Faro originally started the development and engineering was in Germany. Leica, I believe, is Swiss. Z&F, the blue one here, is German. Regal is Austrian, and Trimble actually has some design and development in France or whatever. But in a very small space in Europe, between Austria, Germany, Switzerland, there's a lot of laser scanning technology, and actually there's even a company in Italy. So for whatever reason, there was a lot of technology that was born in that particular area, which is sort of interesting. And how do these things work? Well, this is a little video that I have of an older laser scanner. So it's the first laser scanner that I purchased. Now, this wavelength is not 1550, okay? This one is down at 905 nanometers. And I'm using a full spectrum camera. So it's a converted Nikon camera where I can see up into the infrared. So I can see the beam here, and really it just looks like a very thin beam that's going across the wall. So if I freeze frame one of these frames, you'll see that I have this narrow beam on the wall. So it's a line because of the exposure, okay? So it's streaking across the wall, but actually it's just a dot, and the diameter of the dot is the thickness of that line, okay? So that's basically what you have, like a little laser pointer that's spinning around. And of course, this is probably this is probably quite familiar to many of you here. You've seen the point cloud data and what it collects. So the laser scanner will collect X, Y, Z coordinate data. Now, it actually does it in polar coordinates, but it converts it to X, Y, Z. And then if you're taking photographs, it gets red, green, and blue color channels, and it also collects the intensity of the laser when it returns. So if at full strength, it goes out at 100, you maybe only get 80% back, so you might have a value of 0.8, and some manufacturers have a different range for that intensity. But if you have 20 million points, you have 7 bits of information for each point that you collect. So there's a lot of data there on the point cloud data. But the beauty of the point cloud is that it looks quite familiar. I can see the car, I can see the spill on the ground, I can see the damage. It's not like interpreting a total station survey where it's just points. Okay, you get the idea. I think many of you are familiar with point cloud data today, but let's talk about photogrammetry a little bit here and see what that brings us. So the term photogrammetry itself comes from 3 root words. One is photos, another one is gramma, and the other one is metron. So photos meaning light, okay, like a photon, gramma meaning to write or draw, and then metron meaning to measure. So if I have a light drawing, I basically have a photograph, and then to measure. So really what I am doing with photogrammetry is I'm trying to measure from photographs somehow. Now, of course, photogrammetry means something a little different today because it's evolved into producing 3D models and that sort of thing. And there are many different types of photogrammetry too. So probably the one that most reconstruction people, accident reconstruction people are familiar with is going to be aerial. So get a small drone and push it up in the air and then take some photographs. And that's actually super useful. It's very, very useful. And something this small, like this little drone here. This is my Mavic Mini, the first one. And actually, I'm excited because I just bought a new one. It's arriving tomorrow. So I'll be flying the drone probably this weekend, if not tomorrow. But being able to do roadways. Yeah, terrestrial laser scanning.
Nem mentünk el, aztán még
I think somebody's just chatting there. Maybe we want to mute some of the people. So terrestrial laser scanning for mapping or survey. Now, terrestrial just means that it's done from the ground. So you may have a tripod, you may have something else. But historically, if you were doing terrestrial mapping, they typically are inferring that you're doing mapping or surveying of larger areas. There's also close range photogrammetry, so smaller objects, and then we have micro photogrammetry. So there are people doing some really, really amazing things with even scanning electron microscopes and taking those images and producing 3D models of things which are absolutely invisible to the eye. Very, very interesting stuff. Now, photogrammetry here, this is just an example I did during a training exercise. I was training some police. This is in South Chicago, and there happened to be this building that was being destroyed. So one of the officers, police officers, had a small drone. It was a new drone at the time. I said, hey, let's just play with it for a few minutes. And so this is like a 5-minute flight, and I was just taking photos randomly. I wasn't really thinking about taking creating a photogrammetry model. It was more to test the drone, but there were enough photographs there where I was able to produce some kind of a 3D model. And so the whole idea here is that you want to try and determine the camera position. So where was the camera, where was the drone or the camera of the drone when it took photos? So I can turn that on very quickly here as little blue pyramids, and you'll see them coming up here, the camera position. So when I know these little camera positions, I can now look virtually through that camera, and I can start to triangulate in from a point or to a point from one position to the next position, and you can start to recover some 3D data. Now, I'm showing 3ds Zephyr, which is it's an Italian software product. I know many people are using Pix4D. There's people using Metashape. There's people using all kinds of different products out there. So photogrammetry software, there's no shortage of photogrammetry software out there. You can find free solutions, whatever you like. But the workflow in almost every software is very, very similar. And so the first thing you need to do is obviously take photographs. We could probably have a webinar just on how to take photographs for photogrammetry, because depending on the application and the platform, the environment or whatever, you change the technique. And so when we're doing a roadway from a drone, we use a different technique than when I have, for example, a small piece of evidence or something in a lab in a controlled environment where I can control the lighting or whatever else. Okay, so just know that you have to take a lot of overlapping photos, and getting good coverage is important. Okay, once I do that, there is a feature matching algorithm inside much of the photogrammetry software, and this feature matching algorithm is an important point for Recon 3D and for any photogrammetry. So I'm going to come back to this feature matching, so pay attention to this part. So I have two photos here. They're taken from the drone. They're from slightly different positions, okay? So what the software algorithm will do is it will try to look for high contrast points, then look at its neighboring contrasting points, and then go to another image and see if it finds a match. Now, once you have thousands and thousands of matches, it says, you know what? I think these two photographs are of the same thing because they have very similar relationships. So this uses, usually it uses something called SIFT. It's called Scale Invariant Feature Transform. And that was developed by a gentleman called David Lowe from the University of British Columbia in the late 1990s. And it was really a computer vision problem that they were trying to solve for navigating through rooms and things like that with robots or whatever. But it's a very, very robust algorithm, and it helps to match images which even have a lot of difference. So here, these two images are very close together, but even when you change the angle or the scale or whatever, it can do a pretty good job of matching those features. Now, once you have all these feature matches, it can try to figure out where the camera positions are. And it uses these points, which are often called the sparse point cloud, to determine where the camera positions are. So you have this sort of scattering of points. It doesn't look that great. You can see it starts to approximate the model or the surface that you were dealing with. But this is where You can learn a lot by looking at the sparse point cloud, okay? So you can see how I'm missing most of the roadway in the middle. That tells me something about the photos and the nature of the photos and that sort of thing. But I have enough that I could fix, I could, you know, get all the camera positions. Now, after that, once I've got the camera positions, I can say, hey, go back into the photographs down to the pixel level and now start reconstructing these points. And that's what it's doing here. So it's going back, and now I've got a lot more dense points, and I've got this reconstruction that's coming together. So once I've got these, I can now move on to meshing, and I can say, hey, why do I need 50 million points? If I have a flat surface, I can approximate that surface with some kind of a grid. So you see when I zoomed in here, the points are not breaking apart anymore, okay? They're like a solid piece kind of thing. So it's like draping a sheet over a surface, and there are different techniques for creating this patchwork or this network of patches or meshes. Usually it's a triangular mesh, but then there's even things you can do to make a quad mesh or different things like that. Okay, finally, once you've got that mesh, you want to make it look really good. So there's usually a texturing function, and that texturing goes back to the original photos. It goes down to the pixel level, and it says, hey, inside of this patch, I need to fill that patch with the correct pixels. So it goes back to original images, it picks the best pixels, and then it puts it in on that patch, and you end up with a really nice textured model, okay? Now, there are other things that you need to do. So, for example, there's control points, there's scaling, there's editing. There's always a bunch of things that you have to do with photogrammetry, but this is the basic process, which is similar in most of the programs that are out there. Now, the thing about photogrammetry, for roadways and things that have great texture, like a lot of random texture, it's amazing, okay? So things like dirt and bricks and that sort of thing, awesome. But when you have a shiny car or something which doesn't have a lot of texture, so this car has a little bit, it's got like the numbers and the little targets and things on the windshield, that will reconstruct fairly well. But in the areas that we don't have a lot of texture, well, the photogrammetry starts to break down. It just has a hard time figuring out where those pixels are in 3D. So you can see here, it looked pretty good with the color, but in the mesh, it looks like a disaster. Looks like it has some kind of disease or something. So what we want to do here is obviously get the best mesh that we can get a nice accurate mesh. So whenever somebody sends you a 3D model, you always say, turn off the color. And I just want to see the plain mesh. Now you'll notice here where the door is, you see how I have this empty space here? There's a lot of noise over here, or it just can't produce any points. So if you're trying to mesh that, it has to guess, and it often causes a lot of distortion and a lot of artifacts. Okay, so this is a very, very common problem. And let's look at our evil nemesis here, the dark black shiny car. Okay, so this is like the Darth Vader of to photogrammetry kind of thing. And the reason is, we have to go back to this feature matching. So if I'm looking for a specific point, that point must not move from one photo to the next photo. Because if it's moving, I can't define that point in 3D. Now the camera can move, but the objects that are in it need to be still. So what is the problem with this black surface? Well, I can see the reflection of the back of the fence, of the ground, and everything else. So as I move, and you've probably all seen this, as you take a picture of something that's shiny, like a shiny car, as you move, your reflection moves with it. So things are moving. The pixel appears to be moving, like it has motion or whatever. That is going to cause a lot of problem with photogrammetry. Okay, so we're going to come back to this again. All right, so that was photogrammetry. Now I want to talk about something new, and this is called 3D Gaussian splatting. I'm not going to spend a lot of time on this, but it's probably something that many of you have heard. And Gaussian splatting is just a really photorealistic way of representing or visualizing an object or an environment, whatever it might be. Now, the idea behind Gaussian splatting is that it's not a point, like a pixel, single point. It's actually like an ellipse, okay? Almost like a planar ellipse in space. And it can have a direction, it can have an orientation, it has a certain scale, it has a certain color. So there's a lot of attributes that are associated with this Gaussian splat. And probably the best way to do this is just to show you. So what I have here is, this is an officer police body camera that they wear on their body. So on the left is the body camera, on the right is the resultant Gaussian splat. And you can see that it looks really, really good. And I mean, I was really impressed when I got this particular result. And it just looks super, super realistic. So let me show you what it looks like in the software here. So this is the Gaussian splat, and this is, I'm just rotating around in real time, but I'm going to turn on the points. So these are all the points, like the sparse point cloud that I was just talking about in photogrammetry. The workflow for the Gaussian splat at the beginning is very similar from photogrammetry. You have a number of images, you create the sparse point cloud, but that's where it branches off. It goes and starts to make these splats. So I'm showing you all of the ellipses that are here for the Gaussian splats. And, you know, obviously I wouldn't show those normally, but it makes for quite a photorealistic environment. Now, if you zoom out, you can see that it looks crazy. It looks like, what the heck is this mess? But I wanted to show you this. If you don't photograph or have good coverage in a particular area and you look to the side or something, you start seeing a lot of these crazy artifacts. So you have to be careful with Gaussian splats because you can confuse somebody really, really quickly. All right, we'll leave Gaussian splats there. That's a whole other conversation. Let's get into the iPhone LiDAR, and let me just see where we are on time. So yeah, we're doing really good. Okay, cool. So many of you are familiar with the iPhone, and we've got this little black sensor that's underneath the phone. Let me hold up my phone here. So this is a 16 Pro Max. So it's just a little circle that's down in the corner here. That's a little LiDAR sensor. It's only about 5 millimeters in diameter. But if I were to rip the phone apart, at least on the older phones, you'd see that I have this little tiny device that's in that circle, okay? And it's this guy right here. And it's got these two little circles on it, okay? So what the heck are these two little circles? Well, one of them is a receiver and one of them is an emitter, okay? So it's emitting something and then there's a receiver. Now, before when I talked about LiDAR, I said you have to emit something and then you have to receive something. And so that's what this little sensor is doing for us. So there's a couple of things, and I won't get too deep into it, but it's a pretty if you like electronics and that sort of thing, it's pretty fascinating what they're doing. But they're using something called a SPAD sensor, so single photon avalanche diode. So what you can see here is that there's little a lens, and that lens will focus the light, and then you've got a diode, and there's a number of electronics under here. And basically the idea behind a SPAD sensor is that a single photon will cause an avalanche. What does that mean? Well, just like a little snowball or a small little disturbance on the side of a mountain can cause an avalanche, electronically, if you have a small photon that comes into this sensor, it can create a large output. So you can get a good reading on the output side. And that's what you want, especially when the receiving of the light is not very strong. The sensor that's on this, or the emitter that's on here, is not a super high powerful 20 milliwatt laser like it would be in a laser scanner. It's much lighter than that, so it has to be quite sensitive. But it's using this sort of a SPAD sensor for the receiving part. And then on the emitter part, we're using something called a VCEL, or VEXEL, some people call it VEXEL, a vertical cavity surface emitting laser. And you can see here it has this arrangement of these little circles here, but basically in each one of these spots here, it's going to emit a small dot, okay? And the VEXEL is low power, and it can create these little grids, and it can move them too. So on the iPhone, I'm going to show you this in a second, but it basically moves the pattern around a bit to create an overall larger pattern. Okay, but that's basically what you got there in that little device. Now, I didn't talk about this before, but some laser scanners use time of flight, and some of you are probably familiar with that. So what is it doing for each one of these little dots? What it's going to do is it's going to send out a little pulse for that little, and I'm just talking about a single dot. And when I send out this pulse, just like if I have a flashlight and I turn it off and on, I'm going to start a timer. And that little pulse is going to hit, let's say, the wall. And then once it hits the wall, it's going to bounce back and go back and hit that receiver. And when it hits the receiver, I'm going to stop the timer. So what do I have? Well, I've got time for the round trip, and I have the speed of light, which is known. And I want to find the distance. So speed is equal to distance over time. I rearrange that equation so that the distance is equal to the speed of light times the time. Now the time is the round trip. It's from the sensor to the wall and the wall back. that's twice the distance. So I just have to divide by 2. So it's a pretty simple equation. I can assure you it's much more complicated than that and what they're doing, but that's the basic premise of what time of flight is doing. And what I'm doing here is I'm showing you the pattern in the infrared range. Now, I don't know exactly what wavelength this is because Apple is like crazy secretive about everything. So if you ask them, they never tell you. So, but because I can see it with my full spectrum camera, I know that it's somewhere in the 800 nanometer range. And I have a filter on there that tells me it's above a certain range, let's say. So on the left, you see, this is the older phones. So the iPhone 12 through the iPhone 14, and then on the right it's the iPhone 15 through 17 has this particular pattern right there. So you'll see they're different. One is a little bit finer, a little bit weaker, and the iPhone 15 has larger circles there, little dots, and there's an advantage and disadvantage to each when they upgraded the sensor. I won't get into that right now, but the question is, what does this give us? Well, what that gives us is something called a depth map. So if I have a point on the wall on this hotel room, I want to know how far it is. What I can do is I can convert the image into a depth map. And so for every pixel, I can tell you how far it is from the sensor. So that's an additional piece of information that we didn't have before. So using these depth maps, if I can get a depth map with the LiDAR and combine it with an image, that's very helpful. So let's go back to our evil nemesis here, this guy. So before, if I'm taking pictures from different angles and I have all these reflections and feature matches, which are going to get confused with photogrammetry, if I have a depth map now that says, hey, this point over here at the center of the door, I know that it's 2.3 meters away from the sensor. That is very helpful now, because in the next photo or the next frame that I'm going to be choosing, it says, oh no, now it's 2 meters away. Now it's 1.7 meters away. I have this additional information that I can use in the photogrammetry algorithm to help me recover data that I couldn't get before. Okay, that's the importance of the LiDAR and the depth map. So we're not just using the raw data, the raw distance data, we're converting it to a depth map and using it in the photogrammetry algorithm. Okay, so now knowing all this, what the heck is Recon 3D? Well, basically Recon 3D is something that I began in May of 2022. So yeah, May was just, we had our 4-year anniversary on May 5th this year, which is kind of cool. And the whole idea was to create an app that is tailored for public safety. People that are doing things in forensics, people are doing things for, you know, collision reconstruction, crime scene reconstruction, those types of areas. And that's pretty much what I've focused in on. Now, there's a number of applications that you can use this, and we've done a number of studies here. So crime scenes, collision reconstruction, roadway sections, bullet trajectories, bloodstain pattern analysis, a whole bunch of different things here. And so we have some papers that are published on the website in this area. But let me just run through some examples here just to show you the kind of data or the quality of the data that you can get. So if you want to get close to something, one thing that we do is we provide dense point cloud data. So you're going to have a very difficult time getting, let me go back, well, even I'll leave it on this one. You're going to have a very difficult time finding this level of density with some other apps. They often limit you to a certain resolution. And I know why they do that. And it has to do with, you know, just the difficulty of processing this data and the time as well. But we've left it a little bit open so people can do things that they normally can't. So these are just a clandestine grave. And I showed a body scan. These are like at around 1 millimeter, 2 millimeter resolution. This one is a small bloodstain pattern analysis that I did in my, we have a bloodstain room here where we do some exercises. And so this one is about a 1 millimeter resolution scan that took about 60 seconds to document, not to process. To process takes longer on the cloud, but we've run this through a program called Zone 3D, and we do the analysis there. Of course, collision reconstruction and vehicles. I mean, this is probably the area that Recon 3D is being used most for. So if you're interested in seeing some scans, you can go to the website. It says sample data, and there's a ton of scans you can look at for exteriors, for interiors, for a whole number of different things. For bullet trajectories, we did some studies here. You know, in the area that I work mostly, this is important as well. Forensic engineering, so if you want to capture larger parts and things like that, this can help you, you know, create models and that sort of thing. Fire scenes. So I know that there's people who are working exclusively documenting vehicle fires and things like this. So this is something you can definitely do. It actually does a pretty good job because of the camera sensor that we record video with when we're scanning, and the video or the sensors, the camera sensors that are on the iPhone are actually pretty good. So they, in darker areas, they can raise the exposure a little bit and get you some good data. And this is a larger scene, so something that we captured. I got this in like 6 minutes maybe of documentation time, walking around with a selfie stick and that sort of thing. Small little crash scenario thing, which is kind of cool. And then if you want to do some larger scenes, something like this. This was about a 7-minute scan, and I walk up and down the little ramp here with a selfie stick to document the roadway. Okay, so I don't want to spend a lot of time on this, but just give you a sense of the kinds of things you can do. And there are people that are doing even bigger roadways and such with Recon 3D. So they're pushing the envelope. Recon 3D is really good for vehicles and small scenes, but when you start pushing it really, really big, I've seen some amazing things, but it starts to get a little bit trickier. You really need to start knowing what you're doing when you get these larger areas. Okay, let's go into analysis now. We did the documentation part, right? We talked about photogrammetry, laser scanning, all that stuff, and then bringing it together. So we have the iPhone, but what can you do with this data? I mean, it's great. You have an app, whatever, you scan things, you get data, but who cares? If you can't do anything with the data, it's not all that helpful. So one thing that we did very recently, or most recently, is we did a study on crush. So this was from the Rex conference in, oh boy, when was that? 2023, I think. It was in Orlando. And Leica was a sponsor, so they scanned all these vehicles, but there were a number of people who scanned these vehicles with Recon 3D as well, both pre and post impact. So what we did was a comparison inside of Cloud Compare, comparing these vehicles, the Leica scan to the Recon 3D data. And what we want to know is, or learn from this, is what is the deviation, what is the errors like, that sort of thing. So I'm going to show you a couple of graphs here. And what you'll see is that in the pre-collision, we have about, you can see here, at the 3 centimeter mark, about 98.4% of the points are below the 3 centimeter mark here. So that's pretty good. And we get this peak that's somewhere around, let's say 3 millimeters, something like this. So that's not bad, okay? For the majority of the points are somewhere around 3 millimeters, but as we go up, we can increase. You can see one, even at the 2 centimeter mark, a lot of the points are below 2 centimeters, but at the 3 centimeter threshold, right, very, very close to 98.5% of the points are here. Now, post-collision, this drops down a little bit to about 96%, okay? And the reason for that, there are some reasons for that. One is that the vehicles were moved. So they weren't scanned in the same place, and some of the structure and things like that could have been shifted a little bit. However, it's very, very similar. If you see it here at the peak, we're somewhere around the 5 millimeter mark, something like that. And then the majority of points are below 2 centimeters. And then at the 3 centimeter mark, we're at about 96% of the points. And like I said, some of these differences that are higher up here are due to areas that could not be scanned, and there's a mismatch and things like that. But overall, there's pretty good agreement. Another point here is there was a paper that was published recently. You can get this on Daniel Baumhoff's site, having to do with real-world accuracy, and it was comparing the same data, the Leica scan data and Recon 3D for crush analysis, and looking to see what it actually means. Like, does Recon 3D, if you use it for crush analysis, does it have a difference? And the bottom line is it doesn't. The numbers are so close that it has no effect on the calculation, really. So this paper is freely available. If you type it into Google, real world accuracy issues, Leica scan, or go to Daniel's website, I think you can find it. It's just a PDF you can download if you're interested. Now, other things that we can do here are things like vehicle rigging. So if you scan data, you want to be able to use it in maybe an animation or a simulation or something like this. So inside of Analyzer Pro, what you can do is you can take these scans, bring them in, get them scaled properly, take the wheels out and replace them with wheels here, and that you have a vehicle that you can use inside of AnalyzerPro for whatever you want, and whether it's for simulation or something like that. So that's a really nice feature, and I kind of like the way they do it with the wheels here, how you can just cover them all and then replace them with regular wheels. And so of course, once you got that, well, hey, if I want to just make a really quick animation, grab a Google Maps image, bring it in, and start creating some simple animations for people, I love that. Simplicity is great. That's what you want. I just get a quick idea of what's going on. It's fantastic. Oh, and I didn't talk about this either. I should have probably put a little video in here as well, but one feature of AnalyzerPro that they do a really good job of is meshing the data. So when they bring the point cloud in, they actually mesh the point cloud. And I found that their algorithm is actually really good. They do quite a good job. If you try to do it in a program like Cloud Compare or some other programs, you get a big mess. It's a disaster. I really haven't spoken to Florian about that, but that's one real benefit of AnalyzerPro, being able to mesh it and maybe even export it again and use it in something else. Now, if you don't want to use just a planar surface or something like this, you can bring in a point cloud data. So this point cloud here is meshed in AnalyzerPro, but it was done with my phone. It's just a parking lot that's back here outside my office, and this took me, 7-8 minutes to document, and then I just processed it on the cloud, and then it spits out a point cloud. So when you bring it into AnalyzerPro, you get a mesh, and now you can use this for animations, and the vehicles that you place in here can now adhere to the mesh. So if there's an incline, if there's a bump or whatever, the vehicles can stick with the road surface, which is kind of nice to do, right? So if you have a gradual incline or something like that, it's a great feature to have. So something else that I really like, I love this. So we did a study a couple years ago where we were looking at blind zones. So basically trying to map out what a driver can see. And we did this a couple of ways. So one was using a 360 camera and placing it at the driver's eye position, but we put it at 2 positions. So we put it to the left and we put it to the right. And you can use like an iPad and remotely view that position outside the vehicle, and just with like a survey pole, you can map out the blind zones on the ground. So it's a one-person operation. But the nice part is you can do this digitally. So if you have a scan of the vehicle, you can place light sources inside of the vehicle, and so that's what we have here. So let me play this, and this is from AnalyzerPro, and I believe Florian probably chime in, but this was a relatively newer feature. I think it's been in for a year and a half.
2 years or so.
2 years, yeah. But so this is amazing because look at what it's doing with the mesh. It's projecting these shadows, and these shadows are the blind zones, right, where the driver is going to have some difficulty. And you'll also notice here, there's like a darker and like a lighter shade. And that has to do, if you have 2 light sources, a left and right eye, and they're separated by 5 or 6 centimeters, whatever it might be, you get 2 different shadows that are overlapping. And so the most solid ones here are the ones where you definitely get like a nice solid blind zone. So I love the idea of being able to project this down to the ground. It's very, very useful. Now, there's a whole bunch of other things I know you can do in AnalyzerPro. I am not an expert in AnalyzerPro by any means, but the fact that you can take point cloud data, Recon 3D data, bring it in and do it. I know there are many people doing this inside of AnalyzerPro because they have presented at my Recon 3D user group meeting, and they're showing AnalyzerPro and what they can do with it. And they are much more proficient at it and can speak a lot more intelligently about it than I can. But definitely some great applications inside of AnalyzerPro. Okay, visualization. So when you have, I just showed you a bunch of visualizations actually, right? So the fact that you can present this, but one of the benefits of working in 3D is that the analysis is also in 3D. And so that can be very, very useful. So oftentimes you have to go backwards, okay? So unfortunately, we live in a 3D world, but some people just want a 2-dimensional drawing. And that's something you can do inside of AnalyzerPro or other software, but taking the 3D, going back to 2D, no problem. There are cases where a 2D diagram is just very useful inside of a report. I know that there are still attorneys and people at court that just want a big chart or a big graph and they want to point to it or something on the screen. No problem. 2D can definitely work. There's also these virtual tours now. So many of you have seen these. So this one is from Faro. It's a scene to go. You can bring in the 3D data. You can rotate it around. You can look at it from different perspectives. You can even add in other things like photographs or video, and you can attach it to different points. So this is an offline viewer, so it's you can have it online, for example, if you want to share it with somebody online, or you can also do it offline. So Scene to Go is just one. Leica has a version of this, and there's other software that can do similar things. Now, what about 3D printing? So this is, I have it right here. So this is the photogrammetry model of my car tire. So this was a first shot at it, whatever, but I thought it came out pretty good. You can see the tire tread, right? So we can create other types of visualizations when we cord things in 3D. So this is just a quick example. And I did a terrible job of painting this thing, so you have to forgive me, but you get the idea of what you can do. Now, I didn't have a good example of a roadway in virtual reality, but if you have a roadway and you have a vehicle and damage on a roadway, you could actually bring this into virtual reality. So what you're seeing here is a gentleman here. His name is Dr. Uwe Vossner from the University of Stuttgart, and I've given him some point cloud data, and I did some bloodstain pattern analysis inside of this room. So he's interacting with the data and the results of my analysis in the context of that scene inside of a cave. And it's hard to see a little bit, but there's a little black dot up here, but he's in a box. And on each side of the walls, it's a projector. So what he's seeing is all these things coming out in 3D. It's not what we're seeing or what I'm showing you on the screen. He can see everything in 3D. So imagine if you had a roadway scene and you can now stand or you can sit in the position of a driver. One thing that virtual reality is very useful for is witness perspective, whether it's a crime scene or a driving scene or whatever. So if I can put the driver or someone back in the driver's position, or I can put a witness back on the corner of the road, and I can look down the roadway, and maybe there's a hill or there's a crest, and I can't see past the crest. That's something that we can communicate quite well inside of virtual reality. It's something that we can do. And I had a case. I couldn't show it because it's still an active case, but it would have been perfect for this presentation. But let's just say that I brought the investigators into the virtual reality model on a roadway where there was a vehicle off on the side of the road, and the witness perspective was very important. And they were amazed by what they could see, and it really helped with the level of understanding. So that was really, really helpful. Now, another thing that I would say is I love this idea of virtual models. Now, this is a product that I have. It's called Vision 3D. But the basic idea here is that you can import, this is a photogrammetry model, and then these are point cloud models of vehicles. But you can also tag in all this additional information. And you're looking at the viewer right now. So this is something you can send to somebody in a zip file and they can just run it. So but you can see I can bring up photographs, there's videos, there's documents, and all these sorts of things. You can take measurements. There's a whole number of things that you can do here inside of this virtual viewer. So if you just wanted to send it to a judge or a jury or a client, they can see it all. They can you can put your report in here. You can take measurements, and you can do something called scene states. And what that is, you can set up different scenarios and you can very easily snap to them. So in the right side of my screen, you can see it says state 1, state 2, state 3. I'm doing a measurement right now, and you see I can do it. But now I'm going to change the state. I'm going to move these vehicles to preset positions. And as I flip through them very quickly, I can have, for example, 5 seconds before impact, 3 seconds before impact, 2 seconds before impact, and then very quickly rearrange these vehicles. So it's a very interesting way to combine now this is a meshed model with point cloud data, but we also have a beta right now where we have Gaussian splatting included as well. So very, very interesting for setting up all your different scenarios and then presenting them as a visualization. Okay, It's 10:51 my time, so it's about 50 minutes, and I promised I would only be about 50 minutes, okay? So if you're interested in learning more, obviously AnalyzerPro, get to their website. I do stuff on YouTube where I do like tutorial videos and experiments, and it's all my ADHD stuff that I put on YouTube. Okay, so you can get them here from these links here if you like. And of course, if you have any questions or anything like that, feel free to reach out anytime. So thanks everyone, really appreciate it.
Wow, thank you, Eugene. Your anatomic clock, and also that was an amazing presentation. I've definitely gotten a lot of new appreciation for how you do all of these things. Of course, you kind of know snippets here and there, but you never know how the complete picture all comes together. And you're showing all of this from this iPhone sensor up to the point clouds and then meshing it and all, everything that goes into this. Definitely so much to know about these things. Thank you very much. This was really instructive, and also I think everybody got something new out of this. Yeah, guys, if you have any questions, now is the time.
Yeah, I see some people here that I already know. I can see Philippe there. I can see a couple of other names. So yeah, thanks for being here. I appreciate it. But yeah, if you have any questions about the app or about applications or anything like that, or feel free to chime in. Actually, I know some of you are users out there and you're using it, so feel free to share how you're using it as well. No problem.
Well, I have a question first.
Yes.
I'm just skipping the line here. It's only iPhones that currently have LiDAR sensors, right?
I am hoping that Samsung or another manufacturer will come out with a LiDAR phone, and the reason is if they do it, they're probably going to do it better than Apple, and that also means that, you know, another 50% of the market opens up.
Yeah.
So and you never know, it may end up being a Chinese manufacturer like Huawei, Xiaomi, what's it called, Opus, I can't remember the other name, but it could be a Chinese manufacturer that ends up integrating something like this in the future too. But it would definitely open up the market. So for the moment, you're restricted to the Pro models, Pro and Pro Max models on the phone, and any iPad Pro from 2020 will also have the LiDAR sensor.
Okay. Is there a reason for that? Is the sensor so expensive, or?
I don't know that it's so expensive. I mean, there's millions and millions of these phones out there. So Apple is not, you know, Apple is not spending a lot of these sensors. Probably cost them pennies, really, in the end, you know, based on the mass economics there. But I think just Apple has always been about offering a lower cost alternative for people who want to get into the Apple ecosystem, but don't want to spend, you know, 1,500 euros or a couple of thousand. I'm not sure what the iPhone Pro Max, a 17 Pro Max in Europe, I'm not sure how many euros it costs now, but I know it's not cheap. So so they just offer a Pro version that gives you additional features. And keep in mind, Apple didn't make the sensor for people like you and me, the people doing reconstruction. They made it so people can do augmented reality. They made it so that it can be used for the video, so they can do this cinematic mode, so you can do this spatial photography, so you can do the portrait mode in your photos because it knows where the person is. So Apple, unfortunately, is not thinking about us really, but we're trying to leverage their sensor and get the best data out of it as we can.
That makes sense. So.
Yeah. Trying to see if I can see some of the other people here. Oh, I see Carson. Hey, Carson, very good. Yeah, I can see a few people.
Maximilian is asking, how well does Recon 3D perform in low light conditions or at night?
So you need some lighting. So if it's pitch black, you won't get any data. And part of the reason for that is because it's photogrammetry assisted by LiDAR. So you want to be able to pick up points and get those feature matches. So I have a little, I use a little adapter for my phone. I probably have it. Yeah, it's right here. I can show you. So I have this little phone adapter in my screen, and it has two cold shoe adapters here. And if you want to go high end, these are the Fox Fury lights. And these particular lights, they have like a little, you can change the brightness here, and you can also change the beam with this. You can focus the beam here, so you can do some things, but they're very durable. So at conferences, I throw them because it's a very solid light. But you can go with a cheaper alternative. You can go with just like this is a Amazon newer, whatever they're called. And it's a nice light. You can change the color temperature, but they will also fit in the little things here. So if you put a couple of these lights on and scan at night, just that extra little bit of lighting will help you a lot. If you have a little bit of light, the cameras on the iPhone are quite sensitive, so they'll raise the exposure and get you something quite good. So you can definitely do reconstruction with a little bit of light at night. But if it's pitch black, like if it's very, very dark and you don't have any extra lighting, then it's probably going to fail. Even the flashlight, the torch that's on here, will help you. So even when you don't think you need it. So I don't know, when I gave the presentation of the fire scene, and I was showing that little fire cell, that was actually in San Diego. It was very, very sunny, but you had a very dark shadow. So you know when it's very bright, but you have a very dark shadow, those dark shadows can be helped with some lighting. So I actually had lighting in a very bright scenario because it would lighten the dark shadows. So if you have a car and the hood is open, but it's a dark shadow, if you have lighting on the engine compartment, that will help you get better data for sure. Yep.
Okay, what other questions do we have? Marco asked
Marco, yeah.
If you know anything about NVIDIA's, what is it, LiDAR project?
Can you tell me anything about NVIDIA's photogrammetry project? Oh, geez, everybody's working on something. So, yeah, well, which one specifically? Because they have a, you're talking about the Gaussian splatting stuff? Are you talking about, like even Apple just announced they are implementing a Gaussian splatting viewer for their phones. Now, they haven't done Gaussian splatting yet, but they are talking about a viewer. So we have some ideas with Recon 3D about maybe, well, it's no secret. In the future, if you find Gaussian splatting in Recon 3D, don't be surprised.
Yeah.
We've added it to Vision 3D. But I'll be honest, I've been mostly focusing on Apple recently because they had their worldwide developer conference last week. So that has been my main focus. So I may have to look into this a little bit closer, specifically about their, if it's a new photogrammetry project. I'm not aware of that right now.
Hey, Florian.
Hey.
I have a question. I don't have a question for Eugene. I just want to let the attendees know I've worked with him for a few years, and he has called me back within minutes while on vacation with his family to answer my questions. Amazing customer service. Like actually AnalyzerPro, you guys have been the same way, but Eugene's amazing.
No, thank you, Christopher.
Thank you.
Well, I have a principle and about service, and I may be very old-fashioned this way, but I don't like putting things into forms and then waiting a week before somebody gets back to you. So a lot of times I prefer just to talk to somebody because I understand their problem. I understand what they're working on better. I learn something from them, maybe identify a bug or whatever it might be. So there's always value in speaking to people directly. And the last thing I want is somebody at a scene or somebody trying to document and they're there and they're stuck and they can't do something. So I try to get back to people as quickly as I can. So thank you for noticing, Christopher. Yeah.
Anybody else? Are there any questions?
I have a question for you, Florian.
Yeah, please.
The meshing algorithm that you use, it's I haven't looked at it recently, but you don't close the whole volume on the mesh. So like in Cloud Compare, they use the Poisson meshing algorithm, which actually closes the whole volume. So I don't know. Can you say anything about the meshing algorithm that you guys are using, or you can export? I mean, without giving any secrets away. But
No, I mean,
can you export the model after as a different, like an OBJ or something like this?
yes. It automatically happens. So when you load a laser scan into AnalyzerPro, it will automatically create a mesh, and we will internally only use that mesh. Actually, I have today looked into using pure point clouds for the first time. It's gonna work with the next version too, but we like triangle meshes because it's much easier for the purposes of collision detection with the object. If you don't also have to interpolate the whole surface for the cars to drive on, it's much more efficient for the computer. So you will have much better performance. That's why we have come down to making everything into a mesh as a first step whenever you load something like a point cloud. The meshing algorithm, it's complicated. I don't remember all of the details, I have to say. We also didn't do it alone. I had an external programmer for that. And it's done, we did 2 implementations of that. The first one was single CPU core, which took too long, and then people didn't use it because they had to wait for 10 minutes. And now we have multi-core, and there the difficulty was just stitching the things together properly.
I see.
Yeah, it doesn't have to be a closed mesh.
Okay, and so you mentioned that you're working on like point cloud viewer, so you could just bring in a point cloud. So does that mean, so for example, in the parking lot example, I could have a point cloud and then I could have a mesh like hidden underneath it?
Yeah, that's the plan. Exactly, because we like the mesh for the collision detection, for the surface detection, and for the performance of that, because we need a lot of calculations with car interacting with terrain. And then I would just visually overlay a point cloud, because oftentimes it looks nicer, because oftentimes when you fly a drone, you don't get the side walls of houses, for example, in a very nice way. And then the road surface looks good on the mesh, but then the sides don't look good. So maybe you get the best of both worlds if you just load both, and you don't do collision detection with the point cloud, but the mesh. Yeah.
Okay.
And I'm kind of thinking of the same with the Gaussian splatting at the moment as well. I'm also investigating that for the next version, because I'd also do have a bit of FOMO there, that I'm kind of missing the next big thing. But I haven't gotten anywhere yet, so I don't know yet.
Yeah, it's a strong visualization tool, but it's I'm not convinced yet that it's, well, I shouldn't say that. It depends on how well you reconstruct the Gaussian splat and what the basis of the splat is. So anyway, I will get into it. It's a long discussion, whatever, but I will answer. There's a question from Marco, and I also see somebody from Colombia is here. Hey, welcome from Colombia. So Marco, you asked, did the LiDAR on the iPhone 12 have a higher resolution, more points than the new models? The answer is yes. So the iPhone 12 through 14 had a finer pattern. But what happens is you have to distribute the power to the smaller dots, okay? On the new sensor, well, there were some things happening. So one thing is that the phone was getting very hot if you were scanning for a while. So the new sensor, I believe, is manufactured by Sony. And one of the benefits is a lower power consumption. So it's not going to eat up your battery as quickly, and it's not going to make the phone as hot as quickly. Apple is using some machine learning. So it's actually already fairly low resolution, but it uses some machine learning to upscale the depth map and go from there. So one thing I found with the new sensor, if you want to know about differences, is that if you have a car that has like tinted windows, or if you have a vehicle that has a little bit of dust on the windows, it'll actually close the surface of the window. So you actually get like a closed side window, especially on tinted windows, I found. So there are some advantages there, but it is coarser, it uses less power, but it doesn't seem to have a big effect on the overall result. So that's the good news. Maximilian, what is the maximum range for the iPhone's LiDAR to deliver good results? So the range is about 5 meters. The older sensor was, it depends, like in a sunny day, you would see there might be a little bit of a drop off, but the new sensor has marginally better results. I think I did a video on this. I think it's called on YouTube something about iPhone 12 or 13, something like compared to iPhone 15, and there's just marginally better results. It tends to give you a little bit better return, but let's say 5 meters for a round number. Yeah.
I mean, 5 meters is already very, very good.
Yeah, it's pretty good. It's pretty good already.
Do you see
So-
many advantages that are still with the old school total stations and those things?
Oh yeah, I mean, there's definitely a use for that. So you know, using them for control points, for drones. I mean, the total station, the benefit of the total station or something like this is I can walk 500 meters and take a point, and I don't need anything in between. So there's value in taking, especially for very large scenes. I can take shots with this anywhere. If you have a $70,000 or $80,000 laser scanner, you have to connect the pieces of the puzzle all along the way. You can't just do one scan here and then walk 1,000 meters and then do another scan. They don't connect, right? They will connect if you use this, but they won't connect if you just, do them individually. So there's always going to be a benefit for the total station or for a GNSS unit, something like this. Yeah. Cool.
Okay. Anything else? Anybody else? Okay. Yeah. Well, if not, thank you everybody for your attention and for coming. It was absolutely great. I learned a lot, and I'm also going to check out the ADHD videos from Eugene now from YouTube.
Yeah.
Yeah, thanks, Eugene. You made this very memorable and an amazing learning experience. Big applause.
Hey, thanks everyone. I appreciate your time today. And yeah, if you have any questions, reach out anytime. And thank you, Lisa, for all the help in the organization. And thank you, Florian, for the invitation.
Thanks. And yeah, everybody, check out Recon 3D. The future, past, and present are all in 3D. So incorporate it into your reconstruction. It will improve the quality.
All right.
All right. Bye, guys. See you.
Bye.